characterization. Yeah. Okay. Um, all right, please confirm if you can see the slides. Mac, no, I think Mac will attack. Okay, Mac, no worries. No problem. Take care. Okay, so you can see the slide. Good. So let's continue. To date, we have discussed about the growth of silicon ingot and then preparation of the silicon wafers involving starting from the slicing of the silicon wafers from the ingot and then all the steps involved in preparing the silicon wafers before we start characterizing the wafers. And there are a few things that we have to do in order to characterize the wafers. So these are among the parameters that we usually monitor, but not all the parameters are listed here, not all the specs. Okay, normally when you talk about manufacturing, we're talking about specs or specifications. Okay, so not all the specs are listed on this page, just a couple of among the main parameters. And when we talk about characterizations, generally, we are referring to characterizations not only before the wafer fabrication processes. Even though in this case we are talking about the characterization of the wafers before we start the very first process. But generally, when we talk about characterizations, then it can go, they can go either before the first process in the fabrication or along the way, or in fact at the very end of the fabrication processes. Okay, either it's in the front end or in the back end. So characterization essentially means you try to understand the main properties or the main parameters in the process before you can continue the process. So that implies that if you do the characterizations and you don't get the parameters to be within the specifications, remember we talk about SPC, statistical process control, it's going to be very obvious later on when you join your internship and later your industry, your first career. So people will be talking about process control, especially if you are hired as a process engineer. Okay, so what usually process engineer, so it's all about process sustaining, process improvement, process troubleshooting. Okay, so it's all related to the process. And one scope of your JDs, bila saya sebut JDs, that means job description. So nanti in fact bila you have a look at your internship opportunities and your first career and all those stuff, you always have to go through the JDs of the job descriptions. So JDs maksudnya job description. So I'm just gonna say JD throughout later on. So when you talk about process engineering in general, so it's going to be about process sustaining, troubleshooting, improvement, development, and all this stuff. But essentially, you have to come back to all the important parameters that you have to monitor and see whether they are in control Okay, so as far as SPC is concerned, then we're talking about a control limit and specification limit. Okay, control limit and specification limit or spec limit. So some even say CL and SL. Nanti akan jumpa all these keywords in the next semester, I believe, earliest. Okay, for now, I'll just introduce to you all the relevant parameters that you have to be familiar with before you start browsing for your internship placement, because these are the among the things that you'll see later on: JDs, process controls, CLs, SLs, and we have discussed quite a lot on the first characterization, which I said is among the simplest characterization form that we have in this industry. Okay, so the equipment here looks very simple. The procedures look very simple, but then the information that it can reveal can be very powerful. Okay, it looks very simple. Letak sample bawah scope, letak wafer bawah scope, and inspect. But then you can catch something serious, something significant for the manufacturing process, for the fabrication process, just by inspecting your samples, your wafers, your layers, your whatever, your structures under the microscope, just like what we discussed in this diagram, right? We discussed this last week while comparing that structure to others, okay, on what could have gone wrong in your process. So that's the very first one. Right, so let's move on to the second one. Let me know if anybody has done any AFM for your FYP. So let's just discuss. Anybody has done AFM for your FYP? Mesti ada punya kan? Anyone? Care to share? No? No AFM at all? Okay, not Arisha, okay. Ada ke tak ada ke langsung yang buat AFM? Ataupun tak nak share? Can just share. Okay, AFM, atomic force microscope. Okay, atomic force microscope. So what you have here is essentially, so you have your sample on the stage. So this is the stage. Usually it's vacuum. The sample is held by the vacuum. Vacuum is usually in the center. Okay, vacuum stage. Usually is a vacuum stage. Let me just approve your friend here. Right, it's usually a vacuum stage to hold the sample, especially if your sample is very thin and lightweight. Kalau terlalu ringan, then you characterize and they can move around, right? If you use samples like a glass substrate yang berat, ataupun something yang tebal, yang won't move that easily, so the vacuum will not be so useful. Okay, tapi kalau you guna plastik ke, ataupun some fabric ke, something yang very light and easily move, then the vacuum will be very useful to hold a sample tight. Okay, your sample's there in brown color, and then we have cantilever and tip. So this is the tip that will characterize the surface. Okay, so you have photodiode, you have laser to scan the sample. So this is how it looks like, pretty much like what we have in NOLAB. So anyone has gone to the room where you have UV vis, Hall effect dalam NOLAB? Biasa masuk ke bilik tu? Anyone has done UV vis, Hall effect? Ada? So if you entered that room last time, so AFM will be in the same room as well. So bila masuk tu, AFM will be on the right. Okay, depan dan kanan. So atomic force microscope. So this AFM is used for surface morphological characterization or surface morphology. So when we say surface morphology, that means we use the AFM morphology. Okay. Sometimes we say morphological properties. So it's referring to the surface condition of the sample that we're trying to understand. Okay. So you can scan, say, if you look at this, the sample down here. So we're scanning this sample for a field size of 50 micron. x-axis there, 50 micron. You can see the scale bar there, by 50 micron, right? So 50 by 50 micron squared, if you're talking about the area that we scan. So it's 50 by 50 micron squared. So this size depends on what you're trying to understand. So if your features are very big in the scale of microns, for example, then you have to go perhaps this big in order to get to see the morphological properties of the sample. So kalau your sample, dia punya feature tu, katalah you ada some bumps, kalau ada bump macam ni contoh ni, in this case is very small, tapi yang saya lukis ni agak besar. So in that case, if this dimension is like 5 to 8 micron, 8 to 10 micron perhaps, 8 by 8 micron for example, then you cannot scan your sample in 10 by 10 because you'll just be seeing, kalau you scan 10 by 10 ya, for example, dia ambil square this box you scan, so that's essentially 10 by 10, right? Kalau you guna the same scale bar on X and Y, so if you scan kat situ, then you'll just be seeing one dome, right? One feature, and you cannot make any conclusion based on that 10 by 10 because it's just one feature on the surface and it tells you nothing much. Okay, so that's why you have to pretty much know what sort of features are you looking at if you do the AFM characterization. Therefore, you can customize your scan size to be reasonable with what you're looking at. So in this case, if you want to scan, say, 10 by 10 micron kind of features, so you have to go for, say, 50 by 50 micron squared to be able to see a couple of features on the surface. Then only can make a good conclusion based on what you scan. On the other hand, if you are looking for features in the range of 300 nanometers, perhaps, then 50 by 50 micron squared would be too big. Okay, so in that case, you might just want to go for 10 by 10 micron. So that will be sufficient already to capture to understand the properties of the sample, having features of about 300 400 nanometers. Okay, so it really depends on what do you want to see. So you have to know pretty much what you're expecting to see. Unless kalau you tak ada idea of what will you see on the sample, then you'll just scan anyway and see what you get, and then in the second scan onwards, then only you can tune your field size accordingly, or the scan size. Okay, we call this a scan size or field size. Besides, another parameter that you usually you set will be the resolution of the scan. Resolution. It's not here on this page, but I'll just write it down. So resolution is how small do you want to go between points. Okay, for example, if you scan 50 by 50 micron, in this case, if you go 50 by 50, just like what you have on this image, 512 pixels, dia ada beberapa setting. Usually we use 256 pixel, 512 pixel. So 256 resolution or 512 resolution, sama, pixel size atau resolution is actually referring to the same thing. So if you're scanning 256, if you're using 256 pixels of resolution on this particular field size, so that means you will have 256 points throughout your axis. Katalah you scan 50 by 50, okay? Then you're gonna have along this axis, you're gonna have 256 point. 256 point, okay? Cuba bahagi, kalau you bahagi 50 micron by 256 point, what is the distance between this? Between each point to point distance? Cuba bahagi. Anyone? Can you press your calculator and share in the chat box? What do you get? 50 micron. And then along that 50 micron, you divide that by, well, 256 point means you have 255 spaces. 255 sebab dia ada point ni, maksudnya space between tu ialah 255. Then try to divide that by 255. And let's see how many microns do we get. 50 micron, right? 50 divided by 255. Yep, 0.196 micron. Okay. Yeah, that's close. 0.196 5 or yeah 0.9195 micron. So that means bila you guna 255 sebab 256 resolution, so spaces will be 255. So that means the distance between your current point to the next point will be 0.19 micron, 0.19 micrometer. Okay, so that means you put information and you can catch from the tip. Dia akan scan satu point, say 0, and then the very next point will be 0.19, the very next point will be what, 0.38, and then the very next point will be blah 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 sampailah 50 micron. So let's divide that again with use 50 micron. Now let's divide by 512 or 511 spaces. Okay, divide and share in the chat box. 50 micron divide by 511. Okay, berapa? What do you get? Anyone? Right? 0.097. Kalau nak bunda 0.098 lah. So now you look at the distance between the points, 0.098. In the first case, if you use the resolution of 256, you will only get information every 0.9 micron. Here to here, 0.9 micron micrometer. It means if you use your FM to scan using the tip, you will get the information at this point, but nothing in between. Okay. On the other hand, if you use 512, you get 0.0 the first point, and then 0.09 in between first. Then only you get the next point. Okay. So maknanya you bahagi lagi dua lah you punya resolution tu. So in this case, you are going to get the point in between as well. Okay. You're going to get this point. So as far as the information on the surface is concerned, which one is better? Is it better to do 256 or is it better to do 512 resolution? To get as much information as possible from the surface. Yes, 512, right? Because the more resolution, the higher the resolution you go, of course you can capture more information on the surface. But that comes with a longer scan time. Okay, it's not double, but dia akan tambah quite considerably the time that it takes. I couldn't recall the exact duration, but it's gonna take considerably extra time. But you get extra information from the surface. Okay, this is usually among the parameters that you set. And so what do you get from here? What you get from the AFM is this image. Okay, you can see this image 50 by 50 micron, and then you can see some roughness on the surface, and then you can see on the y-axis here, you can see they have 600 plus, point to 600 plus. So that shows you the maximum point on the feature. Kalau you do cross section, kalau you tengok dari tepi ini, this is 3D ya, this is 3D AFM image. Tapi kalau you buat cross section, tengok dari tepi, then you're gonna plot something like that. That will be, say, your x-axis, 50 micron distance, and then this is your y. In this case, let's put it as z ya, sebab dia kita guna 3-dimensional. Say y is here, x is here, and your z is the height. So if you plot from the cross section, z against x, and then you'll get something like that. Okay, you get to see the profile height. Okay, and in this case, you'll probably be seeing 600 here as your maximum point, 666 in this case. So that's one of the information that you'll get from the FM scan. And another one that you'll get is the roughness of the sample. Okay, roughness of the sample. We normally measure the roughness, or we report the roughness in terms of its root mean square. Root mean square. If you shorten that, if you abbreviate that, so we'll normally call it RMS roughness, or root mean square roughness. So you need to have a look, try to search what does it mean by root mean square, because it involves equation to be able to get the RMS value from the raw data. Okay, raw data that you can put into the equation, calculate across the surface, and then you're going to get your RMS roughness from the feature. Okay, So from here you can see if your sample is very flat, for example, if you scan bare glass substrate ataupun bare silicon substrate, kalau you tak buat apa-apa lagi on the wafer or on the glass, for example, then you just go and scan the AFM, then you'll see a very smooth surface with RMS typically below 3 nanometer. RMS toughness kalau very flat, maybe about 3 nanometer or so, ataupun lesser than that, 1 or 2. So that shows a very flat surface, a very smooth surface. On the other hand, if you're working with features hundreds of nanometers in size, you'll probably be seeing RMS roughness of about 30 to 50 or 100 nanometer, depending on the height, the dimension, the uniformity, and many other factors. But that sort of magnitude is the difference between smooth and rough. You can even get hundreds of nanometers as your RMS roughness as well if you're working with a micro scale, especially. Okay, so try to relate that to the experiments that you've done before. Right, the other characterization that you can do is called SEM. Anybody has done SEM in your FYP? Anybody SEM characterization? Anyone? No one? Mesti ada kan? Tak nak share. So I think some of you have done SEM characterization. Oh, masih bukan. Okay, right. Bukan. Okay, semua bukan. Semua not me ya. Apalah, it's okay. No worries. Okay, so SEM is called scanning electron microscope. If you look at the AFM just now, we use tape and cantilever. Dia akan cantilever tu dia ada tape. Ini cantilever, then you have the tape to scan across the surface. So dia akan feedback, dia akan scan the surface. Kalau dia smooth, then it will not experience any bumps or so much bumps throughout the scan because it's just a smooth surface. Tapi kalau you get like some domes, then dia akan scan macam ni lah. Just to illustrate the mechanism while scanning so that you can appreciate the mechanism. So dia akan jadi macam tu lah. Dia akan scan tinggi rendah, and then dia akan report the value on the screen. It will be detected by the photodiode, and then it will report the image on the screen as the 3D or 2D FM image. Okay. So on the other hand, this one we use electron, okay, electron microscope, scanning electron microscope. So that means in this case we use electron beam, okay, electron beam, in order to characterize the morphology. Still morphology, sama juga macam AFM, but instead of cantilever and tip, we use electron beam to understand the morphology of the surface. Okay, so have a look at the configuration on the left. So you have electron gun, you have condenser lenses, you have reflection falls and all the stuff, final lenses to focus. So eventually you have electron beam to be scanned on the sample. So say if this is your, for example, maybe say ITO on silicon, contoh, katalah your sample here is ITO, then you're going to scan the beam across the ITO layer on silicon to understand how does the ITO look like on the surface, okay, whether it's smooth or rough. And then the information will be deflected, okay, and detected by the detector, and then amplified, and then you'll transfer into image, and then you can see this image, right? So this is how it looks like as a system. Okay, this is the whole setup that we're talking about here. And this is the chamber that you normally put your sample. Okay, katalah your sample ITO on silicon is there, so the beam's coming from the top through all the parts in between in order to get it focused on the samples, and then it will be detected by the detector. It will be reported. Masuk ke sini, keluar image ke sini, image ke sini. Then you're gonna see the morphology of your, say, ITO on silicon. Okay. So those are all the controllers, control bar ataupun dia punya ni untuk control focus, magnification, current, voltage, and all the stuff to be able to get a clear image, right? So one example that you'll you'll probably see is something like this. If you look at the image below, hold on, let me see if we have a scale bar there. Yeah, okay, you can see this image on okay, right, bottom right, you can see the scale bar as well. Look at that scale bar. So there, sorry, that to there is about 100 micron. So each there is about, I think, 10 micron or so, 10 to 20 micron. Okay, about 10 micron, and then that means your feature here is about 10 micron, isn't it? About the size of the separation between each small bar there. So that's probably about 10 micron or so. Okay. So this is one of the features that you'll probably get if you scan. Katalah you ambil this bug ataupun this moth. We don't really call it moth. Kadang-kadang you nak ambil mata butterfly boleh when you sayap if you scan this wing, you'll probably get something like that as well. Okay, so we get many inspiration from the nature. For example, in this case, a butterfly, for example. Kalau you scan, then you'll probably see something like this as well: microstructures or nanostructures. Microstructures atau nanostructures. So if you look at moth eye, I mean, you can check it on moth eye. Mata dia. So it consists of nanostructures. So nanostructure ni, why is it nanostructures? Rupanya it was created in such a way that nanostructures are forming the eyes and some part of the body, so that they are the camouflage punya capability. Camouflage. Apa camouflage? What is camouflage? Apa camouflage? Dia boleh lindungi diri dia boleh menyamar. So color macam daun ke apa, ataupun dia punya pemangsa dia, the prey, will not see the victim easily, because the moment you have microstructures, nanostructures, in some condition, it can reduce light reflection from the body. Okay, bila light incident on the moth, so light reflected from the moth or from the wings, from the eyes, will be a lot less than the incident light. So as a result, the prey cannot see the moth very clearly. So dia akan nampak macam dia menyamar, so ataupun dia tengah apa ni, larikan diri, sembunyikan diri. Okay, so that's the role of the microstructures ataupun nanostructures in this case. So it will help to protect the moth from being attacked by the prey. Okay, so that's one of the hikmah kejadian makhluk-makhluk lain. Right? So, well, this is also used in optical devices. Okay, so that's why I told you now, the nature is full of inspiration. So scientists, they use these microstructures, nanostructures, inspired by the moth eye, in this case, the butterfly or some other insects that have these features, to design our devices. Okay, for example, kalau solar cell, we can also incorporate these microstructures or nanostructures in order to minimize light reflection from the surface cell. Because on a solar cell, you don't want to reflect the incident light back to the atmosphere, because that will be considered as a reflection loss, and you cannot harvest the incident photons and convert it into photo-generated electron hole pairs that will be collected in the outer circuit as current voltage or electricity in essence, right? So kita guna ni, kita guna this inspiration from the nature to design our devices. So in my PhD last time, I used these nanostructures on printed on plastic. right? And the plastic layer, the layer is a couple on glass. Bila you letak plastik tu yang ada nanostructure tu on the glass, nanti I'm going to share with you. I don't have it now, the image. Kalau you tengok glass, you ambil bare glass yang you tak ada apa-apa, then you can see through the glass, right? But then even though you can see through the glass, you can see the glass is there. You pegang glass, but then you can see the glass is there. Okay, bila sampai kat glass lah. On the other hand, if you put these nanostructures, Mohd nanostructures, printed on plastic, pasted on the glass, you pelekatkan layer tu atas glass, you pegang glass yang sama. Ini saya cuba cari balik image yang lama kan. Pegang balik, you're holding the glass with the plastic on, but then you barely see the layer. You barely see the glass between your fingers. Okay, so sebab dia dah minimize reflection at the interface of glass and air. Okay, kalau you pegang tu kan, kita tengok mata kita, cahaya dia lalu melalui cahaya dari sumber cahaya reflected through on our eyes and then traveling to the sample and then reflected back, then we can see the sample, right? So that's how optics work. So in this case, bila the light reflection from the space to is minimized, so you barely see the sample in between. Okay, so that's one of the what I call inspirations from the nature that we use in order to improve our life. In this case, for solar cells and photodetectors, and perhaps some other sensing devices as well. Okay, so microstructures, nanostructures, and these can be characterized on SEM. Right. So another example of characterization, 1037. So we still have time for the first part. It's called particle detection by light scattering. Okay, so yang ni kita pakai a lot in the fab. Okay, a lot in the fab. So the SEM is also being used a lot in the fab, and in this case, particle detection by light scattering, we also use it a lot. So the key here, the physics here is light scattering. So you have your incident light coming to the wafer. Katalah wafer, you ada particles or defects or something unwanted, dust from the atmosphere. So the beam is going to be reflected by the wafer, and then that will be detected by the detector, and this will be detected as the sample is good because the light is reflected specularly. Sebelum ni in optic, have you learned about diffuse and specular reflection? Dalam, I think 215 was it? Optics, second year. Have you learned about this specular reflection and diffuse reflection? Ada tak? Please tell me so that I know whether you know or not. Have you learned about this specular and diffuse reflection in optics or some other previous courses? Anyone? Before we go to the characterization, anyone? Have you learned about this at all, specular or diffuse reflection? Ada ke? Anyone? Or have you come across these words at all? Specular reflection, diffuse reflection? Ada belajar, Haziq? Was it in optics? Lupa dah. Total pass. Cannot remember, okay? So, well, okay, this is a principle. It's based on specular reflection or diffuse reflection. Specular R, diffuse R. Kalau you nak kerja company ataupun later on you nak buat research ke, something related to optics, tak kira lah for various whatever application, spectroscopy perhaps. Okay, applied spectroscopy perhaps, yes. Spectroscopy SEM ni lah kan, 485 kan? Betul? Elective. Okay, try to recall later on kalau you dah belajar or you will learn eventually in spectroscopy. So it's called specular reflection or diffuse reflection. Okay, so I think you're supposed to learn this in optics as well, but I'm not sure. Specular reflection here means bila you have incident light on the on the wafer that is very, very smooth. That's why kita belajar RMS roughness tadi. So say your RMS is like 1 or 2 nanometer, that means super smooth. Maksudnya dia macam effectively like a mirror lah. A mirror yang you tengok muka pagi tu cakap ambul ke pakai tudung ke whatever. So the light is coming at an angle and the light will be reflected at the same angle. Kita belajar kan optik kan? Okay. Theta incident sama dengan theta reflected kan? So for a smooth surface it's true. And if you get the intensity at the same angle detected, so that means your wafer is good because there's no disruption on the surface of the wafer. Okay. On the other hand, the left one is good, and this left hand side is considered specular reflection. Specular reflection ni macam mirror. Kalau you tengok muka dekat cermin kat sebelah saya ni, so saya tengok muka, saya nampak muka saya lah, right? Because the light is specularly reflected at the same angle. Kalau lampu kat atas, reflected, datang kat masuk mata saya nampak muka saya kan? So that's the principle. So on the other hand, if the mirror is diffuse in nature, any of you, or maybe I think all of you, some of you, or majority of you have gone through, waktu kecil-kecil lu pernah masuk fun fair tak? Pernah masuk fun fair? Pernah tengok tak fun fair, I don't know, rumah hantu ke whatever, I couldn't remember. Satu part yang perhaps you tengok cermin tu, you nampak muka you disrupted in some way. Pernah tak masuk tengok muka kecil ke, muka besar ke? Okay lah, okay. Muka, tak nampak muka ke, right? Okay, so kenapa you tak nampak muka? Mungkin at that point tak ada upper ke, okay? So at that point, perhaps in some condition, perhaps the mirror is designed in such a way that you have more of diffuse component than specular component. Okay, so incident light yang you dapat tu, the principle dia, kalau you dapat 100%, kalau you reflected 100% to the detector, just like in the first case, so we call that as specularly reflected ataupun specular reflection, just like the way mirror works. On the other hand, if you're looking into a distorted mirror, you nampak muka jadi pelik, whatever. So you'll probably have some components of the incident light is diffusely reflected. Okay, so in this case, I relate to the wafer fab lah. So you have your incident light here, and then you have some light specularly reflected, but due to the presence of the defects on the surface, some of the light will be diffusely reflected. Diffusely reflected here means the reflected light will not be reflected at the same angle like the incident light. So the theta R here is no longer similar to theta I, tak sama. In fact, you're going to get multiple reflection at multiple angles due to the presence of something on the surface or disruption on the surface. In this case, kalau fun fair tu, the mirror itself is distorted somehow. Tapi kalau wafer ni is due to the presence of the defects, multiple defects across the wafer, that will cause diffusely reflected light to the detector. Okay, so due to this mechanism, so the optic is this. Okay, so kalau you nak faham kenapa you belajar all these optics, so itulah dia punya among the applications that you can appreciate at this point. So you will, due to this, you can see the by light scattering. This is called light scattering. Bila they scatter into multiple angle due to the presence of particle, we call that diffuse reflection, and that is the light scattering into multiple angle. Kalau tak ada scattering, incident angle sama dengan reflected angle. No scattering. Kalau incident is like this, and you diffuse into multiple angles, multiple locations, multiple places, then you call that scattering. And you call that mechanism, in essence, as diffuse reflection due to the presence of particles. And as a result, you can see this hot spot, you can see this another hot spot, you can see this particle presence on the surface, contamination. And if you look at this wafer map, sebenarnya dalam sistem tu kita akan dapat this wafer map after the scan. Kita panggil wafer map dalam fab. I still remember the terms wafer map. So sometimes if you have particle issues in your equipment, in your process, in your chemicals, in your gases, so this is one of the characterizations that you have to do in the fab. Not only before the wafer process, not only during the wafer characterization, but also during the semiconductor fabrication processes. You can also do this to make sure that your wafer is super clean before you start the deposition as well. So that's why I said when we talk about characterization, it's not only before or during the fabrication, but along the way, along the process where it is relevant. So in this case, it's called wafer map. So you will see particles everywhere. Okay, particles everywhere. So in this case, is this wafer good or is this wafer bad? Is it a clean wafer or is it a dirty wafer? Yeah, dirty, isn't it? It's very straightforward, right? So in some process, well, it depends on the process. We control this. Sometimes you can tolerate these defects, but they have to be of certain size, certain nanometer, for example, or certain X to certain micrometer, but it has to be less than, say, 10 counts. Count, kita panggil bilangan ya, counts. You have to have like 10 dots maximum, ataupun 5 counts maximum. So if you look at this, like what, thousands of different counts, 1,000 counts or hundreds of counts, so of course this one will fail the process. Okay, kalau you scan, katalah you punya spec, that's why I come back to the spec. If your spec says during the scan the count has to be less than 10, but when you scan you have like 535, say contoh. So what will happen is this process, this equipment, this gas, this chemical will be shut down right away. Okay, will be shut down. So implication dia shut down. Process shut down, equipment shut down, tool shut down, whatever. Dalam fab kita panggil equipment tu tool. Tool. It's actually referring to equipment, but the language that we use in the fab is tool. Kalau you cakap your tool is okay, so that means your equipment is okay. Okay, so the language that we use is tool. Tool down, tool up, tool down, tool up, tool down. Tool problem, process problem. So the implication in this case, if you see 535, your process, your equipment, your whatever related to this particular layer will be shut down. Okay, so bila shut down apa jadi? So equipment, the PE, the process engineers will be inside to troubleshoot. Equipment engineers will be inside to troubleshoot. Then your quality control will come, chase after you to troubleshoot the root cause and to summarize, and your boss will come after you to make sure that the issue here, the particle contamination, will not happen again in the future. So you need to have something like preventive action in mind. Okay, bukan only we have two things when you do the troubleshooting. You have corrective actions. So saya incorporate here all the languages from the fab that you have to be familiar with. These are among the things that we say in the fab. Corrective action. Corrective is one. Another one is preventive action. Preventive, sorry for the handwriting. Corrective means you have to correct the problem there and then, problem solved, done. But that will not guarantee the problem from happening again tomorrow or tonight or next month or next year or next week, right? So bila you are the engineer in charge of this particular process or equipment, the boss will come to you and ask, what are your corrective actions done to solve the problem, and what are the preventive actions that you will do in order to prevent the problem from recurring tonight, tomorrow, next week, next month, next year, so on and so forth, right? So you always have to have this mindset: corrective actions, preventive action. Kalau you ada corrective action je, preventive action tak ada, that will not be enough, right? Because you solve the problem now, but then the problem may come again tonight. So kalau ada lagi problem tonight, then you will be called tonight to go into the fab and troubleshoot the problem and solve the problem. Okay, so for the wafer map, you can use this equipment, defect inspection. So KLA Tenko is one of the famous suppliers for this particular role. So we can use this for defect inspection. So you will essentially see the wafer maps now. So the notch is here. We learned notch last time. So you can pull out all the dotted scan from this wafer. So wafer kat sini. So you have 25 wafers. So scan to the stage. Dekat dalam ni, it will be scanned inside. It will report the map there. So that will be your wafer map that you've seen on the previous page. Okay, the map here. Okay, So that's pretty much what you'll get from this defect inspection. So those are morphologies, and you can have more morphologies, more morphological characterizations like optical scope, SEM, AFM, SPM, STM, scanning probe microscope, scanning tunneling microscope. Saya tunjuk kat you just a couple of characterizations that we have only. Won't be able to show everything, but I'll let you know the category. Yeah? So first, morphological characterization. So the second category is called electrical characterization. So we have 4-point probe. Anyone has used 4-point probe before? Anyone? Pernah pakai ya 4-point probe? A very simple 4 probe, 4 needle. Pernah pakai? Then the 4 needle, very simple one. You have this needle here on the stage. Ada 4 needle. Okay. So where you will pass the current to the 2 needles. You can see the circuit there. Then you'll measure the voltage on the other 2. Okay. So from here you can get your resistivity of the sample. So resistivity is rho, and you can also get your sheet resistance, R sheet, rho and R sheet of the sample. Say you are characterizing silicon thin film on glass, for example. So you can then get your rho, you can get your sheet resistance, and then you can also estimate from the rho. We learned last time in 386, you can then estimate the doping concentration, right? So if you look at the chart, the rho against doping or doping against rho, you can get some chart, some data to correlate. If your rho is this much, then that reflects doping concentration of say 10, 16, 17, 18, so on and so forth. It's a very simple tool, just a very short time to characterize. Okay, so your rho, so equation is here, V over I times 2 pi S to get your ohm CM. So you can get the information like whether it's right, the doping level, the carrier separation, carrier mobility. But this one is the second one. The second one is called Hall effect. We learned this as well in 386, right? So your first characterization method for electrical is 4-point probe. Your second one is Hall effect. Hall effect is more comprehensive if you compare to 4-point probe, because it can tell you the carrier mobility, the doping type, whether it's P type or N type, and then you can get your mu E or mu H. You can also get your rho, you can also get your R sheet. Okay, there are more information provided by Hall effect. So we've learned this one in 386, so I won't be repeating this. So all the stuff. So we've learned about this Van der Pijl method as well. So where you need to have 4 contacts on the sample. So for example, if this is your silicon wafer, for example, silicon, then you need to use 4-point contacts, for example, aluminium or silver or aluminium, for example, depending on what you want to get, right? And then nail the metal contacts on the sample and do the Van der Pijl measurement, do the Hall effect measurement. Okay, another characterization you can do is FTIR. Anyone has done FTIR before? Fourier transform infrared spectroscopy. Anyone has done? Before we stop for the first session. Ada? So we have FTIR in NOLAB as well. If you have entered one room in front of an XRD room, so there's an FTIR there, and also a PL system. FTIR is a Fourier transform infrared spectroscopy, and a PL photoluminescence, right? So in FTIR, you will characterize transmission, reflection, absorption in your samples in the infrared region. Okay, infrared region. You can do this using UV-vis as well, but then UV-vis is limited to UV visible. Mungkin ada yang dah pernah pakai. You can do this only within UV, visible, and near infrared, but you couldn't go into mid onwards, right? Mid infrared onwards, you have to go to FTIR. So examples of the band or the profile that you can get if you measure transmission. So within this infrared region, you get a wave number. Then you can compare your samples with another samples in this case. Okay. So another one is transmission electron microscope, which is a more advanced version if you compare to scanning electron microscope. Okay. This is TEM. We don't have it in physics, but we do have it in bio, School of Biological Science, and we have another one in SERC. SERC is in engineering, engineering campus. So we have TM here, bio and SERC. We don't have it in physics. So it looks similar to SEM, but it is more complicated in terms of the configuration, the way it works, sample preparation. It's harder. Okay, it's harder to do. So using electron beam as well, and then you have condenser system in the middle, and then you have condenser aperture, you have sample holder here in between, you have a couple of lenses, you have projection system, and then the imaging will be at the back. Okay, so if you compare your TM operation with SEM on the right, so let's look at the difference. So you can tell by the configuration of TM versus SEM. Looking at the configuration alone, you can tell already that TM is more complicated, okay, in terms of what it has in the vertical chamber before you get your image projected on the screen, okay. So those are the differences between left and right. Okay, so the typical settings that we use in TM: beam size of about 30 amp, and then beam voltage depending on the samples, resolution, but then it's based on transmitted electron. So if you use SEM, you're gonna get your image based on, say, this is your sample. So your sample will be reflecting light and scattering the light, and the light will the electron beam, not the light, electron beam will be detected. So it's based on scattering. Okay, scattering is the principle, scattering, back scattering, but on TM is based on transmitted electron. Transmitted electron maksudnya, boleh tengok sampel kat sini, electrons coming from the top. Okay, this guy, electrons coming from the top as well, and but this for TM, electrons coming from the top, but you will get the electron measured at the back of the sample. Yes, get electron to has to penetrate through the sample. For SEM, dia tak akan penetrate, okay? So dia akan just be deflected, scattered, and detected and reported as an image. On the other hand, if it's transmitted electron, transmission electron, so as the name implies, transmission, maknanya dia kena transmit through the sample. So that means in this case, the sample has to be very, very thin in order for the electron beam to be transmitted across. Dia kan lalu kat belakang sample. So that makes the sample preparation a lot harder, because if your sample is too thick, then the transmission of the electron will not happen, and there is no image detected and reported on the screen. Okay, so that's why mata kat sini tengok ni ada kat belakang. So because it detects the electrons transmitted through the sample. Okay, so it's based on combination of transmitted electron. Okay, so this is among the image. Kalau normally if you have features below, we're gonna finish our first session shortly. We finish this. So normally if you have features below 100 nanometer, you have to go for TEM already. Okay, so if you have features above 100 nanometer, you can still use SEM. SEM pun dia ada dia punya level. So the one that we use in our lab is called field emission SEM. That's better than a typical SEM, right? Tapi general rule dia lebih kurang kalau you ada features particles or features or textures or whatever that is above 100 nanometer, you can still do on SEM. Tapi kalau it's approaching 100 nanometer like 120, 150, maybe the resolution will not be as good on SEM, and it's about time to go for TM. Okay. Tapi kalau features you, in this case, you can look at the scale bar, it's 50 nanometer, and this like quantum dots, for example, quantum dots. So kalau tengok satu size tu, that's about, I think about 10 nanometer or so in diameter. So that's about that size. So that's probably a 10 nanometer or so. This one slightly bigger, but more or less they are like 10 to 20 nanometers. So you have to do this on TEM already because you won't be able to see this on SEM. Kalau you bawa sampel ni on SEM, you won't see anything at all because the resolution is way smaller in order to be seen by SEM, in order to be characterized by SEM. Okay, so then you have to go to TM for your characterizations. So later on, if you're working on areas that require you to work with quantum dots or nanoparticles with size below 100 nanometer, then you'll be dealing with a lot of TM. So the difference, so just like what we have discussed on the previous page, and then you try to figure out, okay? Apa beza antara SEM and TM? Okay, so that's done for the first part of today. So we finished the wafer characterizations, and bear in mind that these are not everything. This is not every single characterization that we normally have. These are only among the characterizations that we have. So we normally have something morphological characterization, electrical characterization, optical characterization. Banyak lagi ya yang saya tak sempat cover semua. But they are usually categorized as one group: morphology, optical, electrical, chemical, whatever. Right? So any questions for now based on the first part? Can you follow so far? Okay, no questions? Okay, so the next one, let's have a break for, I think, 10 minutes. Apa 10 minutes? It's sekarang 11:02. On my screen is 11:02. Let's come back at 11:10. Okay, 11:10. So you can have your breakfast or coffee or something. Toilet ke? Come back 11:10. We'll continue with clean room. Okay, what is clean room? So I'll just unshare this and turn off my camera. Then we'll come back 11:10. Inshallah, we'll continue with clean room. Okay, bye for now. Assalamualaikum. Okay, everyone's back. Better? Right, good. Let me share with you the slides on Cleanroom. Hold on. Cleanroom. Okay, Cleanroom. Oh, not annotate. Sorry, kan annotate lah. Sorry. Disable. Okay. Okay, can you see the screen? The slides. Alrighty. Alrighty. Few years ago, I think 2 or 3 years ago, you punya batch pernah pergi ke Siltera ke? Was it your batch or your senior? Ah, okay, dah pernah pergi lah, right? During, I think 2018 or so. Oh, tak pergi eh? Tapi ada yang pergi lah, eh? Kan ikut sekali, right? So, that was you were in your second year ke? Second year or first year, I couldn't remember. Oh, first year, okay. Alright, right. Yang waktu tu saya pergi sekali ke? Dr. Wan Mariam, saya tak ingat lah. Saya, okay, saya ada sekali ya. Alright. Okay, so with that batch lah dengan apa ni? Siapa nama tu? Saya sudah tu. Izian eh? Izian punya batch kan? Okay, so basically you've got some, okay, Izian. So you've got some ideas of the clean room and you've watched the videos on clean room presented by Siltera last time. So sebelum ni I think about 5 years onwards, selalunya kalau ada visit during my time when I was in Siltera, kalau ada student visit ataupun university visit, usually memang Siltera bawa masuk dalam fab. Okay, bawa masuk dalam fab lah. So that means you have to gown up, you have to dress up in the bunny suit. We call that bunny suit, baju yang angkasawan tu. Kita panggil bunny suit. So you have to gown up, and then you'll be brought into the fab for a tour of say 1 hour or so. Tapi lately memang Siltera tak bawa masuk. I don't know why. Maybe ada certain limitations ke. Control the tak dapat masuk kan? Yeah, I remember that time cuma ada video presentation saja kan. So which is quite unfortunate, tapi no choice lah sebab company tak bagi masuk. Yeah, during my time memang ada trip kalau student USM datang ke UITM datang ke, memang ada fab tour lah by person in charge yang akan bawa student memang inside the fab. So then you'll see all the equipments, the environment, the pace of people working in there, the meeting sometimes, you know, kadang-kadang ada meeting juga, meeting tergempar to decide on certain things. The situation, the overall situation in the fab that cannot be easily told atau easily presented dalam slides. Okay, so saya akan cerita kat you just some of the things, but for the full appreciation still, kalau you tengok video pun, I'll probably say you can appreciate 50% of the actual things inside the fab. Kalau you tengok video mana-mana pun, TSMC ke Intel ke GF ke, that will just be like 50% or perhaps below 50%. So bila you masuk fab, you tengok, you dapat tour yourself, then you see, okay. In fact, saya punya student previously yang memang belajar 487, yang dapat internship dekat Siltera, so among their first messages to me, bila dia start internship dan dia masuk fab, so lepas tu dia akan text. So I've got a few of this, a couple of times, a couple of batches. So sekarang baru saya dapat appreciate how does it look like based on what we learned in 487. Okay, so kita akan belajar all this stuff, but then it's just on the slides and a bit of experience sharing from me. But still, that will just be 50% good, perhaps. Okay. Bila dah masuk, you tengok equipment, you nampak the situation tu, you will, baru you teringat, oh slide 487, oh clean room, oh ini characterization, oh belajar ni, lithography, etching, so on, wafer breakage, ataupun equipment shutdown, ataupun people, bergaduh each other to decide on certain things. You'll see that, right? So dalam fab, for your information, dalam meeting, just before we start, we do have every meeting, we do have meetings every day, department meeting. So if I was in photolithography, I was a litho engineer back then. So we had a meeting 8 to 9 every day, 8 to 9 every day. So that's department meeting. So after 9 will be another meeting among bosses. Okay, manager has another meeting. So for perhaps another half an hour or so. Tapi department meeting will be every day 1 hour at least. And in the meeting, just to give you some ideas, dalam meeting tu ada manufacturing team, ada engineering team, ada, so well, normally manufacturing and engineering. And dalam meeting ni memang kita akan discuss what happened yesterday. Okay, what happened? Okay, imagine you have process engineers, you have equipment engineers, you have manufacturing engineers from manufacturing department. Tapi dalam proses team, dalam department punya team tu, ada process engineer, equipment engineer. Tapi and satu team ni ada manufacturing. Okay, so and if you talk about wafer fab, normally the department is categorized by the process name. Okay, so for example, if you talk about lithography process, then it is one department, etching process, one department, implantation process, another department, thin film, so on and so forth. Dan dalam satu department, say we're talking about lithography department, dalam department there'll be like 30, 40 engineers and technicians and so on. So there'll be equipment engineers, equipment engineers, process engineers, application engineers, development engineers. So daripada engineer, daripada fresh sampailah ke manager lah, manager. Okay, and then above that will be director. Onwards lah, director ni yang tengok multiple departments. So in the meeting, we discussed what happened yesterday. What happened to your process? What happened to your equipment yesterday? The last 24 hours. It's always the last 24 hours, right? So kalau ada semalam ada equipment shutdown, process shutdown, a particle problem, ataupun printing ada issue, ataupun ada chemical contamination, ataupun wafer breakage, range of different issues will be discussed in that particular 1 hour meeting. Okay. And you will see later on if you get to do your internship in wafer fab ataupun mana-mana semiconductor electronic industry back end or front end, you will see manufacturing and engineering team ni dia akan sentiasa bergaduh lah macam manufacturing cakap kenapa you tak ni, dan engineering cakap you don't give us the time to do the troubleshooting and so on, that's why we couldn't do it. Manufacturing cakap dah bagi banyak kali tapi still tak solve. So you'll see this kind of culture. So we quarrel every day. 1 hour tu memang macam you won't believe it. Nanti bila you dah masuk ke dalam internship ni, you will believe me, okay? But then the firefighting culture ni, even though it's every day, but the firefighting culture is completely professional. Okay, it's part of things that you have to learn and get from this course, even though it's not technical. So the firefighting is completely professional. So what I mean by that is, kita bergaduh dengan manufacturing or engineering. If you're on manufacturing, I'm on engineering, then saya bergaduh dengan you. So our quarrel too is not between you and me. It's between the thing, the topic that we discussed, the shutdown, the particles. So it's completely professional. Dia bukan you ambil hati ke, saya ambil hati ke, no. We quarrel like nobody business. We fight like nobody business. Like I don't know you, you don't know me. But after the meeting, pukul 9 kita pergi cafe, kita breakfast sekali. Right? So it's completely professional. It's not like take it to the heart or whatever. So you will appreciate this later on when you join semiconductor industry, in particular wafer fab. Back end dia punya nature is a bit it's a bit more relaxed, but not that relaxed. Tapi dia tak se-complicated front end. Wafer fab lebih complicated from if you compare to back end. Okay, this is real. This is what we know. So about front end, dia punya nature is more high tech, and you don't get to see many things naked eyes. For example, and optics, you print guna light and everything. It's not like what you can see easily. If you compare to backend is more like packaging, testing. You punya chip tu dah ready. You dah nampak chip, nampak kaki dia, nampak probing. You know, it's very visible. So that makes the complication a lot lesser if you compare to front end. Front end banyak imaginary kind of things. You just see results, but in between you just have to guess. You have to intelligently guess what's actually happening or what could be happening and what could prevent the issues from happening again in the future. Okay, so that's why. So you will appreciate this later on. Some fresh students usually akan terkejut lah bila you join internship ataupun your first job. You masuk first meeting, tiba-tiba you think of this kind of firefighting like you've never seen before. You mungkin akan culture shock sikit lah. So salah satu cara saya cuba kurangkan you punya culture shock is by preparing your mindset in the right way so that you masuk tu you know what to expect. That's very important. If you just qualified for the post and then you are accepted, you're hired, but you don't know what to expect, you'll probably be shocked later on. Culture shock in its own way, fab kind of way, right? So trust me, you'll see this later on. Nanti kalau you rasa this is not true, then come back to me after your internship. Let me know. Okay, so that's some preamp thing. So we have learned about characterization in our previous topic. Okay, let's just recap a few things. So why do we need to characterize incoming wafers in this case? Kenapa kita perlu characterize incoming wafers before we start our first process? Anyone? Let's just recap for a few minutes before we continue with Cleanroom. You can unmute yourself and also write down in the chat box why characterize. Yep, go ahead.
To detect defect.
Okay, to detect defects before the first process. All right, thank you. Any other? Another point, why characterize? Can't we just use the wafers, assuming that everything is good? Anyone? Faris? How about you, Faris? Any points? Okay. Anyone else? It's okay. Just share your understanding. Alia? Kenapa kita characterize, Alia? We know the specs already on the package that states so. Can we just believe the spec and proceed accordingly? Quality analysis, okay. Can't we just believe the specs? I mean, the specs are there anyway, right? On the package, say kalau you assume wafer dah ada package, and so, everything's written there. So why do we have to still bother? Why characterize in this case? Alia, anything? Sari, Izyani? Anything? Why characterize? Okay, Amirul cannot because not all parts are according to the specs. Okay, Sari to measure electrical properties and morphology. Okay, Fatin to detect the presence of impurities. Say if you are a supplier quality engineer, you jaga incoming wafers. For example, before we start our very first process, can't we just believe the specs written on the package, wafer package? Tak boleh percaya ke? If we cannot believe the specs, that means the manufacturer has a problem, right? Maknanya dia wrongly declare the spec lah. the parameter is wrongly declared. It says the wafers are very clean, but they are not very clean. So in this case, why don't we just believe in the specs? It's a bit complicated. In some cases, kadang-kadang kita punya wafer tu kita tak tukar pun. We still use the very same wafers, the very same specs that we have been using for the last 7 years, perhaps. And we have done all the characterizations early in the phase, 7 years. And well, there's no reason to characterize again because by right, the wafers should be of the same quality. But somewhere down the line, maybe, I don't know, some fluctuation or something in the factory of the supplier before the wafers are supplied to our team, to our factory. I don't know, maybe they have some glitches that has caused some problems on the wafers. So that means from time to time, you might have to impose some periodic characterizations in order to make sure that the wafers are really clean and really within the specs before you run your first process. So that's why characterizations are important. Right, next one, what characterizations can be used to study the surface? So we've done this now, AFM, SEM, all the stuff, particle defect inspection, you can do that as well. Working principle of AFM, you just go and check out yourself. Okay, so clean room. Okay, what is clean room? Anyone would like to define a clean room? What is your understanding of clean room so far? Apa masuk clean room? Anyone? Boleh unmute yourself. Kita discuss, it's okay. It doesn't have to be 100% accurate. Anyone? Sanitize diri, sanitization. Sanitary room without any dust, okay? Any other? Room without dust, sanitize. Control environment, okay? Control environment, no dust. Lagi ada lagi? Clean room. Alright, so control environment, kebersihan, room without dust, sanitize diri, okay? So everything is true. Good. So clean room, kalau ikut the simple definition is bilik bersih lah. Clean plus room lah, bilik yang ruang yang bersih. Right. So that's how you have to dress up when you are in clean room. So you can see this on the left, the blue. Some people call this smoke. Some people, well, normally we call this bunny suit. Bunny suit. Bunny. Oh, sorry. Yep, bunny suit. Okay. Smurf. Okay. All right. So some fabs ada dia pakai color code color code ada, if I'm not mistaken, Silvera pakai biru for vendors. Ada color code, ada pakai hijau and so on and so forth. Contractor ke, vendor ke. So in this case, vendor means the supplier of our machines that's supposed to be working in the fab at the same time. Okay, so dalam fab, dalam clean room, it's not only the employees working, right? It's also the vendors working. Vendor yang datang regularly, datang to do some maintenance or troubleshooting or to do some projects with the engineers. Okay, so it's not only the engineers, technicians, it's not only the employees of the factory, but it's also the vendors. So therefore, the bunny suit needs to be color coded. Okay, so usually white ni for employee lah. So saya cakap tentang Silvera, I'm not sure about others. So mungkin dia orang ada different color juga lah. So yep, so this is how it looks like. And if you look at the one on the right, so this guy is inspecting or checking wafers. So you nampak ni wafer ni. So those are the wafers. Typically 25 of those in a pot. So this is the rack yang ada dalam pot. Pot. So normally you have like that pot and you have like 25 wafers altogether, right? So okay. A clean room environment is designed to reduce contamination of processes and materials, right? So Arisha said in a controlled environment with no dust, and some others said no dust, space without dust, accomplished by removing or reducing contamination sources, right? So it's designed to reduce contamination of processes and materials. This is accomplished by removing or reducing contamination sources. Sumber contamination tu kita reduce or kita eliminate altogether, right? So that's how it looks like in the picture. The environment, you have your bunny suit, you have your goggles, you have your kasut pun ada. Overshoes ni you have to pakai kat luar, pakai baju tu. And there's even a step, a list of steps that you have to follow in order to wear your bunny suit. You tak boleh simply pakai kasut dulu ataupun hood dulu. So dia ada step. You'll be trained on that when you join your internship or if you join the company. So there are the fixed step that you have to follow through to get your gowning correctly. Typically used in manufacturing or scientific research, or in this case, we're talking about wafer fab. And control environment that has low level of pollutants such as dust, airborne, micro aerosol particles, and vapors. A control environment of contamination that is specified by the number of particles. So we control by number of particles per meter cube. Okay, 1 meter kali 1 meter kali 1 meter has to have less number of particles of certain size. Okay, that's a key thing. Okay, number of particles per meter cube at a specific particle size. So that means in this box 1 meter times 1 meter times 1 meter perlu ada certain number of particles saja of specific size. Later on, you can look at the YouTube link down there, Introduction to Cleanroom, understand? So for perspective, to put things into perspective, ambient air outside, kalau you keluar dekat, say, apa ni, Sungai Dua ke, ataupun apa ni, Bayar Lepas ke, depending on the area of course, in a typical city environment, Georgetown ke, typically contains about 35 million particles per meter cube. Yeah, 35 millions of particles per meter cube. 1 meter times 1 meter times 1 meter. Satu box. With size 0.5 mm and larger in diameter. Okay. Kalau you pergi Georgetown, so perhaps this is the typical number of particles that you will probably find in 1 meter cube. 35 million particles. Okay, with sizes 0.5 mm and larger, corresponding to ISO 9. Dia ada ISO ni, clean room dia ada level lah. How clean is the room? How clean is the clean room? There are multiple levels, and you have a standard to govern that, to monitor that, right? So the other level we're going to see later on, which is at the lowest level of clean room standard. So you're going to see later on on the link. So it's a dirty world out there. So if you go to the outside, smoke and particles and dust, and kalau pergi kat kawasan factory yang low tech lagilah kotor kan. Kalau pergi yang high tech mungkin dia control the emission with certain specifications and so on. But you go to kilang kayu ke, kawasan kilang yang tak ada control, memang it's very very dirty, right? It's a dirty world out there. So uncountable particles in air with all sizes, shapes, and properties. So if you talk about this environment, outdoor world, kalau you nak fabricate your device, transistor, which is small and fragile. So you're talking about, say, 100 nanometer of size, and you are dealing with hundreds of microns and mm and cm of particle outside. Just imagine kalau 5.5 by 5 micron particles in the SEM image down here drops on your MOSFET with gate length of, say, 100 nanometer. Ready? So your gate is like 100 nanometer. Just imagine. Then you have these particle drops on. So it's going to cover the whole thing, right? It's going to cover the whole thing. And in fact, your adjacent transistors and so on and so forth. So particle can go ke atas and it will kill the devices. Okay, it will kill the devices. Yes, dirty words. Therefore, the fabrication cannot be done in our typical environment. In fact, kalau kita bukan in the city pun, if you're just in my room, for example, then that just won't work because it's still a dirty work, right? It's still a dirty work. Dust and everything, and aerosols, and many others. Okay, so therefore the fabrication has to be done in a clean room environment. In fact, kalau you tengok dekat clean room environment pun, the wafers will need to sit inside a pot. Okay, we call that as a mini environment. Okay, so pot ni, so this is another language that you have to learn for a fab. This is wafer pot. So kiri kanan ada tempat pegang, macam you pegang pot, you pegang bakul contoh. Dalam dia ada wafer, 25 wafers for example. So wafer ni, wafer ni, pot ni kita handle dalam clean room kan, kita tak bawa dia keluar ke parking ke whatever. So it's a clean room environment. So the ambient is in clean room. And even then, the wafers cannot survive. So the wafers need to be in another environment, in a clean room environment. So we call that as mini environment. Mini environment dalam clean room. So clean dalam clean lah. Mini environment sebab dia isolated from the clean room itself, even though the room is already clean, even though the fab is already clean, the atmosphere is already clean. So still, the wafers need to be handled inside a pot that we call it mini environment. Okay. So nanti kalau you masuk fab, then this is among the language that you will say day in and day out. Right? So clean room overview used in semiconductor manufacturing, biotechnology, life sciences, because these fields are all sensitive to environmental contamination. Okay, environmental contamination. So to be able to enter a clean room, so kalau you are hired to do your internship in a fab, for example, then you will not be given a permission to enter the clean room just yet until you finish and passed a training. So you're gonna go through certain training online ataupun face to face by HR development team, and then you'll need to sit for an exam, pass the exam with certain minimum points ataupun mungkin 100% correct kot, 100% mark, then only you'll pass and be given permission in your card. Okay, maknanya you nak scan nanti you ada permission already. Kalau you tak ada permission, you are not trained, you don't pass the test, the exam. So kalau you scan pun, it won't open the gate for you, right? It won't open the gate. So you'll need to have your permission. So if you're hired, typically I can easily say 3 weeks to a month of duration is purely for training. Okay, mungkin you will need to go every single day, full hours, maybe half day at least for a couple of days in a week for like 1 month to be able to complete the basic training in order for you to operate as an intern or as an employee. Kalau you tak complete tu, you can operate yet because you cannot access this software, you can access that software, you cannot open certain folders and stuff like that. Then you won't be able to do the job properly, right? So for you to enter the clean room, the staff need to enter and leave through airlocks environment. So katalah I cannot illustrate in this case. Katalah this lady engineer, for example, she's coming from the other side. Katalah dia dari luar, dari office nak masuk clean room masuk ke sini. So clean room will be the inside, on the inside. So dalam kelas I can just show you easily, but online ni susah sikit Clean room. Clean room is on the inside and office is from there, for example. Office. So this lady engineer is coming into the clean room. So you notice there are 2 doors, door on the inside and door on the outside. Okay. So 2 pintu and these 2 doors are not opening at the same time. So katalah you belum masuk dari sana, the moment you open the other door from the outside, daripada sana, then this door will automatically be locked. The inside door will automatically be locked. Okay, so that means this operation will ensure total isolation of the fab, of the clean room with the other environment. The other environment will be the outside environment, office ke, jalan ke, lift ke, whatever, on the outside before the outside door. But this environment will be protected in the form of locking mechanism. We call that airlocks. Okay, so bila buka pintu sana, you masuk dengan you punya bunny suit tu, you tutup pintu luar, then you will have to go through an air shower. Kena mandi mandi tak bukan mandi air, bukan air air shower. You have to be showered with air, you have to be cleaned in your bunny suit. So dia adalah I think about 20 seconds or so, akan ada air yang perch on your hair and keliling badan, you have to be like something like this. Dan angkat tangan semua. Dia ada prosedur, you'll be trained on this later on eventually. But you have to pusing and be clean and flushed. Make sure you're all clean for like 20 seconds or so. After the air shower finishes, then only the inside door will open. Okay, barulah you can open this door while the outside door is locked. Maknanya there's no person coming at the same time. Dia kena tunggu you habis, you be processed, then only you come out, you enter the clean room this side, then you lock, you tutup balik pintu ni, tutup balik, then only the mechanism for the second guy will start. Dia akan repeat the very same process. So at all times, the clean room will be protected from the typical environment by this airlock mechanism. Okay, so you can have a look there. PPEs are all worn, hood dah pakai, face mask is worn. So orang yang kerja fab, orang yang biasa kerja fab ataupun any clean room environment, before COVID memang we've been wearing all the PPEs already, just like the frontliners punya baju tu. So it's worn already inside the fab. So it's not something new. It's just that it's not worn outside. It's worn inside the building, right? Kalau sekarang frontliner pakai kat luar kan, deal with the patients and everything. Face mask, glove, boots and coverall. So coverall ni dia punya bunny suit lah. Some people say bunny suit, some coveralls. Right? So that's how you enter the environment. So let's go on for another 10 minutes, I think. So this is a schematic of the clean room. If you look at the room as a box, okay, this is the whole thing. The clean room. So say you're coming from the outside. Kata you nak masuk from the outside. You nak masuk from the outside to inside. Okay. So air from outside is filtered to exclude dust, and the air is inside is constantly recirculated through high efficiency particulate air. We call that HEPA filter. So air dalam clean room tu dia akan circulated. Dia akan coming from the filter on the ceiling. Dia akan turun bawah in the form of laminar flow. Laminar flow means uniform flow. Laminar flow. So dekat lantai dia akan ada lubang-lubang. So lantai, a proper fab will have lubang. We call that perforated floors. Perforated floors. Tile tapi ada lubang-lubang kecil. Kenapa lubang-lubang kecil? Kenapa lubang-lubang kecil? Because you want to ensure that the flow from the inside, from the ceiling to downward is laminar. Maknanya dia masuk secara laminar uniform. If you don't have any perforated floors, maksudnya you pakai tile yang biasa, then dia akan jadi turbulence. Dia akan ada bounces on the floor because there's no way to go, right? So perforated floor is to help the flow to be laminar. Masuk dia akan circulated dekat tepi ni ya. So you can see here it's coming from the HEPA down there. So dia akan ada lubang-lubang dekat floor. It's going to be recirculated through the wall. Naik balik kat sini, kat tepi, turun balik. So it's a closed loop kind of circulation of air, right? And upper filter, depending on the space. Some using upper, some HEPA. So the clean room itself is capped at a positive pressure. Apa maksud positive pressure? So positive pressure simply means bila you nak masuk fab, okay, this is the whole fab, katanya contoh. So that means the pressure on the inside of the fab is higher than on the outside of the fab. Okay, you can see here the pressure is plus and plus plus, tapi pressure kat luar ni zero. So that means the first room A here has a plus pressure, room B here has a plus pressure. Apa maksudnya? Maksudnya if you open the door from the outside, pressure zero, katalah you guna pressure zero as a reference. Bila you buka pintu tu, you will feel that the door is, bila you buka je pintu, the air will be pushing towards your face. Air akan datang daripada dalam keluar sebab pressure kat dalam lebih tinggi pressure kat luar. Because your room A has a plus pressure compared to your zero pressure from the outside. Okay? So bila air keluar, dia akan push all the particles to the outside and maintain the clean room environment. Just imagine if the pressure doesn't work. Katalah dia punya pressure sama apa jadi, The moment you open the door, the transfer particles can transfer between outside and room A because they punya pressure sama kan. So that's the use of the pressure difference in this case. Okay, so the same goes to if you want to move from room A to room B. Bila pintu buka ya, you scan pintu buka, and you'll feel like the air is rushing towards your face because the pressure of room B is plus plus in comparison to your current pressure, which is plus. Okay, so then particle daripada B akan transfer to A akan transfer to 0. So that's how you maintain a clean room. So you can't afford to have a similar pressure everywhere in the building, right? Because you need to maintain the clean room environment. So HVAC system control humidity to low levels. Air conditioning system, HVAC air conditioning system to control humidity at low levels, such that extra equipment or ionizers is necessary to prevent electrostatic discharge problem. So you will need to control your temperature, your humidity, your many other parameters in the environment. Okay, let's go through for another few minutes. So let's compare the flow of the air for the two environments. So the one on the left has a turbulent flow. Okay. So mungkin in this case, dia punya lantai dia taliang tak ada lubang. So you can see that the air is coming from the top, but you have turbulence on the floor. So turbulence, kalau you ada particle on the floor, the particle will be brought at certain height and interact with your devices. Okay, and sangkut dekat bunny suit, then you will then handle the wafers, and the particles will drop on the wafers, and then you're gonna have thousands of particles on a wafer map later on when you do the scan. On the other hand, if you have laminar flow, laminar is on the right, turbulence on the left, so the flow will be very uniform. Okay, so normally kita ada perforated floor here, and the flow will be something like that. It'll be circulated like that, right? So it'll go down there, it'll go up, circulated on the sides. Okay, so then that will minimize the risk of particles flowing around in the space and contaminating the wafers. So let's go on for another 2-3 pages. So clean rooms are classified by how clean the air is, right? So it's classified by how clean the air is, just like our comparison to the typical cities now, 35 millions of particles per meter cube with certain sizes. And if you look at this table, for example, you can see ISO 1 to ISO 9. Okay. For example, if you look at ISO number 1, you can also compare this with another standard, which is called 209E standard, which defines the class of clean room by the class number. Class number 1, class 1, class 10, class 100, class 1000, class 10,000, class 100,000, and room air. Room air is considered as ISO 9 lah, ataupun room air lah. So you can choose either one of the standard, but typically if you talk about if you talk in the fab, people will say that this is class 1, class 10 environment. Okay, so we'll normally use this one a lot later on. So let's look at class 1. Class 1, what is the requirement of class 1? So you need to maximum particles of size 0.1 micron. Dia punya limit at 1000 only, right? So maximum particles per meter cube. It can only afford to have particles above or equals to 1 micron up to 1000 counts only. Okay, kalau dia more than that, it will fail the class. It will fail the audit, right? So 237 above 0.2 micron, 102 above 0.3 micron, 35 only above 0.5 micron in order to be qualified as classroom environment. Okay, so then if you go down to class 10 dia lebih kotor lah. It's not dirty in that sense, but if you compare to class 1, of course, it's a bit relaxed in terms of the particle requirement. So if you look at class 10, for example, if you can have up to 1000 for 0.1 micron of particles, you can afford to have up to 10,000 for class 10. So that means if you talk about this particle size, so it's 10,000 more relaxed in terms of the specifications, right? And the same goes to other particle size as well. They can follow, but then you can see that the zeros are added more and more to the to the specifications, right? And these numbers are maintained, control, maintained, audited by QA. Quality department dia akan QA, some say QC, dia akan ada weekly monitoring, monthly monitoring, dia akan datang dan measure the particle size for particular volume of space in certain department, dalam certain area of in the fab, litho ke etching ke implant ke diffusion ke whatever. So then compared to the specifications that the space needs to adhere to, okay? So dia akan maintain lah. So you can see now the class 1 is the cleanest one, and if you go down here, then it's going dirtier and dirtier, okay? Dirtier and dirtier. Okay, last page. Contamination. How do we get contamination in the clean room? Macam mana boleh ada contamination? So we get that a lot from particles. The first one is particles. Okay, so dari mana datang particle? From the dust, from the skin kita, walaupun kita dah pakai bunny suit and everything, from the hair, if you expose, then of course you will induce particle formation. And this one, makeup. Kalau you join the training nanti dalam internship ataupun kerja, you will be informed about this. Makeup is a big no-no, right? It's a big no-no. If you are into makeup for your daily work, then fab is not for you. Okay, right? It's a big no-no. Huh? You won't find a single lady in the clean room wearing makeup because it's a no-no. You won't be allowed, right? Kalau if you're caught, then you'll be punished. Because it's a big no-no in the fab. You will induce particle formation. Okay. Glad to hear that, right? Okay. Taklah kalau some of you mungkin yang nak berjanguk sikit kan, you have into makeup, nak every day you have to wear makeup to work, to do your stuff, then it's not for you, clean room. Not allowed, big no-no, pangkah siap. Right, so chemicals, some other sources of contamination from oil, from grease. Tangan kita pun kadang-kadang peluh, kadang-kadang you handle things tak basuh properly, then that's why you have to wear gloves. Metal ions, perfume also big no-no. If you're into perfume ataupun ada audit, then you smell like wearing perfume, then habis, kena pangkah, cannot. So I need to be very straightforward here. You'll be trained on this eventually. Kalau you're working in the fab ataupun back-end industry that requires certain level of cleanliness in the space. Biological sources like bacteria, fungi, rodents. Pernah jumpa dalam fab when I was in Saudi Arabia, saya pernah ada cicak mati somewhere near the equipment. We didn't know how did it end up there, but well, it's funny, but yeah, it has to be controlled. Radiation, ultraviolet light, and some other because of interaction with the material that we're going to use to perform the process. Okay, so these are among the contamination sources. Almost time. Okay, let me just finish in 2 slides. Okay, particle characteristics. If you talk about particles, 50 micron particles are visible. Okay, are visible to some extent. Average human hair is 100 microns. So rambut kita kalau kita pakai the hairnet, then it's 100 micron thick. That's what we discussed last time as well. Humans, we generate more than 1 times 10 to the 5 particles per minute when motionless. You tak buat apa, you are fully down, you are motionless, you duduk senyap. You cuba duduk senyap 1 minit, you are actually generating how much is 1 times 10 to the 5? 100,000 of particles. 100,000 particles per minute. Some more you are motionless. You tak buat apa tau, duduk diam ya. Tak tahu, duduk senyap, berkoyap 1 minit, 100,000 particles generated by us human. Okay. So humans can generate 1 million particles per minute. So if you walk in a clean room, then you are actually generating at the same time 1 million particles per minute. Walking. So are we clean then, in that sense? Are we clean in that sense? Kita mungkin bersih lah, but then we are not clean to the wafers. We're not clean to the devices that we want to fabricate. In fact, when I was trained last time, I was told that this is a bit funny, but then it's true though. I was told that we are gowned, we are, you know, we are fully protected, we are fully gowned and everything, in order to protect the wafers from us, not us from the wafers. Maksudnya kita gown ni nak jaga wafer tu sebenarnya, nak jaga device tu daripada rosak, from not functioning. Kita nak jaga device, that's why we have to gown up. It's not like you have to gown up in order to protect yourself against something. You are protecting the wafers from you. So you are the risk, you are the danger. So this is one of the things that you will be trained on later on. You might find this funny, but it's true, right? So we are gowned all together in order to protect the devices from us. So we are the risk, we are the threat. Okay. Okay, last slide. Contamination sources. So this is chips from Silterra back then. Now they look different because of various other devices being manufactured. So this is what we have inside Silterra as well. So you see, so that's the wafers, that's the pot. So you don't get to hold the wafers with your fingers, with your, even though while you're wearing gloves, you're holding the wafers by using vacuum handler or vacuum wand, right? Vacuum wand. Some call it vacuum handler. Kita on vacuum battery, yeah, battery operated. Then on they can hold, then you can flip to see what happens to the front side, to the rear side, any scratches, any visible particles or anything weird to the surface and stuff like that. So we pick up the wafers from the pot using the wand or the handler, right? Then you handle and see. So contamination sources, people, 75% of the sources. So 3/4 of contamination comes from us, right? Ventilation of the room, the space, the clean room, the pressure, all those stuff, circulation, turbulence or laminar, 15%. Room structure, the design, 5%. Equipment, the movement, the robot, the automation system, well, 5%, right? But all in all, we are the major contributor or the contamination sources in the fab, in the clean room, 75%. Okay, so I think I'm just gonna stop here. It's almost 12 already, so it's almost 2 hours. So I'm going to continue with every single group of the contamination sources in our next class next week. Okay. Right. Any questions for now? So anyone now don't want to work in the fab already? Anyone turn off already? Ladies? Ada yang memang turn down the offer. Of course you're not wearing makeup, right, Nazik? Are you? I believe you're not. I hope you're not. Okay. Bedak pun tak boleh ya? Bedak pun tak boleh ya? No. So pakai ke, Aziz? Are you sure? Okay, right. So yeah, well, some people really turn down the offer from the fab just because they cannot wear makeup. It's real, okay? Bukan saya punya own ni, memang ada yang tak nak, because I have to wear makeup. I have to wear makeup. I cannot survive. For example, tapi ada case, so it's real. So that's why I make it clearly a big no. If you are into makeup and all those stuff, then of course the fab is not for you. The clean room is not for you because you will not be allowed to do that during your working time. Okay. Pakai makeup pun buat apa kan pakai mask. Yeah, exactly. Good. You're wearing it, but then only these areas visible, right? And then these all masks and the rest all protected. And if you're working on something like equipment, you have to change pumps, do robot teaching. You akan berpeluh kat dalam to some extent. Saya dulu tukar pump and robot and cabut ni when I was doing equipment engineering job. So you will be berpeluh, you'll be sweating inside. Really, you'll be sweating inside if you're handling something big. Kalau you buat process or some handling simple stuff, then probably you won't be sweating because it's quite cold in there. Temperature and humidity are maintained well. But if you're working on equipment, you angkat pump besar, robot, tukar ni, then you'll be sweating inside. So kalau you pakai makeup, it's gonna melt anyway. So yep. All right. So see you next Monday then. Any other questions? All good? Right then. So I hope at this point you can already appreciate what is a clean room and what does it take to work in a clean room. Okay, so we're gonna elaborate later on in terms of contamination sources and whatnot. So after the clean room, we're gonna go into our first process, thermal oxidation on the bare wafer. Okay, so if no other question, then that's it for today. Bye bye. Thank you. Assalamu alaikum, and stay safe.